Good day, students. We're finally in chapter 10. 9 was a long one. Quick one. A, B, and C. I'll do A here. The main point is that after working with linear equations and linear models for the past week or so in class, you probably think that the only thing out there is a linear model, and that's simply not the case. When you collect data and you're looking at two variables, the relationship between those two variables, there are other patterns that you'll see. So we'll explore that in this lesson. There's a couple of approaches to dealing with nonlinear data, and one of them is called re-expressing your data or transforming your data. We won't cover that here in Math 127, and basically what we'd like to do is, in this lesson 10, just give you a taste of what you could do. Most of these types of skill set would come in a Stat 2 course, but we're just going to do a quick introduction. All right, so lesson 10, nonlinear models. The principle, here's a word I'm guessing most of you have never heard of. If you've heard it, good. The word's parsimony. Parsimony. And so let me read this for you. The principle of parsimony should be applied when choosing a model to fit your data. Remember that models are never perfect. We're trying to give a best guess for the pattern in the population. Parsimony means that we should tend to pick the simplest model that does the job. Okay, so one benefit of a linear model is a linear model is very simple. People understand a straight line relationship. The coefficients are easy to interpret, so the slope in a linear model has a nice, easy interpretation that people without statistical backgrounds can understand. The y-intercept has a nice, simple interpretation. And so the theory of, or the principle of parsimony would say, look, if linear will do the job, we should pick linear. Okay, it's simple. Unfortunately, not everything's linearly related. It's very inappropriate to fit a linear equation to curved data. And like I said in the intro, let's look at some curved models here, and we'll just start with an example. Okay, world population is increasing over time, but it's not linearly. Okay, so what we have here is we have year, 1900, and we'll jump up by decades, up to 2010. Population is given in billions. Back in 1900, there were 1.65 billion people on the planet, and if you just jump ahead to the year 2010, almost 7 billion people. So I think I read a statistic recently on the internet that there are currently more people alive on the planet right now than all the people that have ever been on the planet who are currently dead. There's more people alive now than the number of people currently dead. Population's increasing, but it's increasing at an increasing rate. So it's speeding up. As we move forward in time, the population is increasing at an increasing rate. It's got to be a graph here if I flip the slide. You've got it in your notes in case this isn't showing up on the video. I did put the straight line in here to show you that, boy, if you were really you didn't really look at the data, does the straight line capture what's happening? Well, as you move forward in time, there is an increasing positive pattern, but it's slow at first. And as I get to the 1960s, 1970s, 80s, it sort of takes off, right? Like a rocket ship that just blasts off into space. That curved pattern increasing at an increasing rate is called exponential growth. It's incorrect to fit the straight line. It's not capturing the pattern in the data. Remember, we had said when you're doing a linear model, we need to check a residual plot, and you're looking for the residual plot to show no pattern. If there's no pattern in the residual plot, that confirms that a linear model was the right choice. Do you see a pattern in this residual plot? Well, of course you do. Here's the line at 0, always the mean of the residuals, and there is a clear pattern in the residual plot. This clear pattern tells us that linear is not a good choice. Linear is not a good model choice. Pretty darn obvious to see it in the original scatter plot, but for sure, we look at the residual plot, we can see that linear is not a good choice. Okay, so what is the good choice? Here's the data again up at the top. I guess if we flip the page, it's an exponential function. an exponential function is good for modeling phenomena that either increase at an increasing rate or decrease at a decreasing rate. So things are either speeding up or slowing down as you move left to right across the page. Okay? In general, an exponential function looks like this. I'll use the y and x. So y equals, usually there's a coefficient out front. We'll just label it as a times b, and then exponential function. The variable x, our independent variable or our explanatory variable, shows up in the exponent up here. So y equals a times b raised up to the x power. Couple restrictions on this b number. B cannot be equal to 1. If b is equal to 1, then 1 raised to any power is just always going to be 1. So this function would look like a horizontal line. And secondly, b has to be greater than 0. Okay, so do write those in your notes. We do need that to have the official form. Now, depending on the value of b, whether b is greater than 1 or sort of squeezed in between 0 and 1, we'll either get that exponential growth or that exponential decay. Okay? It says it right here on the slide, getting ahead of myself. First bullet point, if that base b exceeds 1, we have exponential growth. Exponential growth, that's the world population. Things are speeding up. Okay? If that base b, remember it can't be negative, if it's squeezed in between 0 and 1, which is like a fraction, right, then we'll have what's called exponential decay. Exponential decay means as you move forward in time, things are decreasing, but at a decreasing rate. They're sort of slowing down as you move forward. I do believe I have an example of that, and then we'll practice in the next video. Light intensity example. That's the amount of visible light decreases exponentially with depth as we travel below the surface of a body of water. So for this example, we're up in some lake up in Minnesota, and we're taking a measurement. I go down 5 feet below the surface. I take a measurement with my photometer here. This measures how much light is coming down into the water. I go down 10 feet. The measurement is 7.5 LMs. And all the way down, if we go 40 feet below the surface, how much light's getting down there. Okay, you can see the picture in your notes of the scatter plot. It's exponential decay. As you go further down, it slows down in terms of how much light's getting down there. Okay. Now, one thing to note, the correlation between the variables is r equals negative 0.898. That's a pretty strong negative correlation. It's telling us these variables are related, but what we need to do is look at that scatter plots. I can't just look at this correlation in isolation and say, well, it must be linear and fit a linear model. Okay? Without looking at the graph, you might think we have a slam dunk linear relationship. Now you've got it in front of you. You've seen the punchline here. Let me just make these show up on the video a little bit better. On my x-axis is depth in feet, so here's really close to the surface, and then here's 40 feet below the surface. And you can see as I move just off of the surface, this is decreasing quickly, and then it tapers off. There's your exponential decay. Okay? Of course, I threw the linear model in here. Do not fit a linear model. Take a look at the residual plot next door. If you flatten this out at 0, you're going to see that parabola shape. Here it is. This is a residual plot, the one on the right in your notes. Do you see a pattern? The answer is yes. So I'm on the right here. Is there a pattern in the residual plot? Clearly there is. Right? You can draw a nice parabola shape if you wanted to play connect the dots. Pattern in the residual plot. Yes. What does that tell us? It tells us do not fit linear model. make sure there's no questions I'm supposed to answer. At the bottom, there's not. Okay, so just to summarize this, other models exist besides linear models. The two that we'll look at, Kim Shepard's going to look at exponentials in more detail in the next video, and then we'll finish up with quadratics, just to sort of show you what's out there besides those straight lines. So, thanks for watching, and we'll see you in class.